Yes, fine.
Welcome everyone in this room, everyone on chat to this hybrid combinatoric seminar. We're very pleased to have Swee Hong Chan from UCLA, who many of you know, and if you don't, you were in pandemic probably. So he'll tell us about Combinatorial Atlas and the rest. Welcome, Swee Hong.
Thank you very much for the introduction. And also, I would like to thank everybody, both in the audience and in the online, to come despite the pandemic. So today's talk, the main character is the log-concave inequalities. So here is one quick definition of log-concave sequence. So we say that a sequence, let's say there's real numbers, non-negative real numbers, A1, A2, up to AN. We say that this sequence is log-concave if for every k from 1 to n minus 1, the kth number square is greater than the product of the k plus 1 number and k minus 1 number. For example, this sequence is log-concave. And if you, for example, let's take the third number, 9. 9 square is 81. It's greater than 4 times 15, which is 60. The same applies to all other numbers in this sequence. And another reason, one reason why this is called a log-concave is because suppose that you take the log of this sequence. Then it turns out that this is the same as saying that this log sequence is concave. It's also known that if you take a log-concave sequence and the sequence has no internal zeros, that everything in between is always positive, then this sequence is actually unimodal, which means that at first it will go up until some point, and then after that it will go down. That's like how COVID was supposed to be in our ideal world. Okay? And here is one famous example of a log-concave sequence, the binomial coefficients. This is, and this sequence is log-concave because if you take the ratios of the binomial coefficients, the ak squared divided by ak plus 1 times ak minus 1, this ratio by direct computation is equal to 1 plus 1 over k times 1 plus 1 over n minus k. Because of the choice of k, which is like greater than 0, less than n, this number is always greater than 1. That is how we know this sequence is log-concave. And by the way, it might be a good idea to try to remember this term here, because like soon we will see it again. That's a little bit of a spoiler. Okay, another famous log-concave sequence is coming from permutations. So let AK be the number of permutations of n elements with k inversions. But remember that inversion of a permutation is a pair I and j, such that I is less than j, but pi I is greater than pi j. So somehow you change the ordering. That's why it's called inversion. And already for this sequence, you cannot do direct computation. And the best way, not the best way, but one most common way to prove this sequence to be log-concave is to write the generating function. When you do this generating function, it turns out that it has a very nice formula. You can write it as a product of the following polynomials: 1 plus x, 1 plus x plus x squared, 1 plus x plus x cubed, x squared plus x cubed, and so on. And the important part here is that in all of these polynomials, the sequence form a log-concave sequence. Sorry, the coefficients form a log-concave sequence. It's known that if you take the product of such polynomial, this property is preserved. The product of log-concave polynomials is again log-concave polynomials. And that is how we prove that this original sequence is log-concave. And here you already see that proving log-concave seems to be not easy. You cannot, in this sequence, you already need to use something sophisticated, at least not that you cannot do by direct computation. Up to this part, is everybody happy with log-concave sequence? Do you feel like it's your friend now? No? Okay. Okay, so in fact, log-concave sequence is not only for these two sequences. It appears in many different parts of mathematics. I believe that it's possible to have one semester of class, UCLA we use 1/4 or maybe 2/4 of classes only on log-concave sequence, only on different parts of mathematics. But of course, today I only have like 60 minutes. I don't have 2/4 of classes. That's why let me focus only on two things today: matroids and posets. And let me start with matroid. So here is a quick recap on what is a matroid. It comes with two data: a ground set X, which in this example is the collection of edges of this graph, and a collection of this thing that we call the independent sets, which is the subsets of the ground set, such that it must satisfy two properties. The first one is called the hereditary property. That means that the subset of an independent set is again independent. For example, let's say that these two blue edges, they form an independent set. Hereditary means that if I delete any one of the edges, let's say I delete this one, the resulting set is again independent. The second one is called the exchange property, which says that if you have two independent sets, one larger than another, for example, this red independent set is smaller than this blue independent set, then you can find one of the blue edges, move it into the red set, and the resulting set is again independent. That is what is known as the exchange property. So these properties may sound a bit abstract, but it actually have many concrete examples. And perhaps the most quintessential example of matroid is what we call the graphical metroid. This is where the ground set is a set of edges of a graph, and the independent set is the collection of edges in a forest of G. Another example is what we call the realizable metroids. This is where the ground set is a finite set of vectors of a field. Can be finite, can be infinite field. And I, the independent set, is obviously from the name, is a set of linearly independent vectors, the set of linearly independent vectors. And in fact, the graphical metroid is actually a special case of realizable metroids. Graphical metroid is where the vectors are the vectors in the adjacency matrix that's realizable over any field. Okay? So they are concrete objects. And there are many conjectures about log concavity in metroid, but today I will only focus on one of them, the Mason's conjecture, which is actually stated in the year 1972. And what happened is that Mason looked at this sequence, Ik, where Ik is a number of independent sets of size k, and he said that, okay, let's try to make conjecture on this sequence, that this sequence is log concave. And not only and he made this conjecture as 3 inequalities ordered from the weakest to the strongest. The first one simply say that the sequence I1, I2, I3, and up to In is log concave. But Mason is a bit greedy. He said that, okay, let's not stop there. Let's go even further. He said that, how about if I add this constant 1 + 1 over k on the right side? Maybe it still works. Oh, okay, he tried to do that, put it as a conjecture. And he said that, okay, why not even go further? Let's add another term, 1 + 1 over n minus k. And this, the third one, is called the strongest form of Mason's conjecture. And some of you here might say that, okay, or might think that, why is it that we put this very weird term, 1 + 1 over k plus 1 + 1 over n minus k? Where does it come from? This actually has a very good combinatorial interpretation. That remember that this constant 1 + 1 over k times 1 + 1 over n minus k, we have seen that before in the very beginning. That is the ratio of these binomial coefficients. So Mason tree is the same as saying this thing that we call the ultra-log-concavity or the binomial log-concavity, which is that if you rescale your Ik, your sequence, by the binomial coefficients, the resulting sequence is still log-concave. That is what it means to be a binomial log-concave or ultra-log-concave. And Mason believed that this is the case for the independent sets. One of the reasons is because he knows that, oh, if every k + 1 subset of your matroid is independent, in this case, ik is equal to n choose k, ik plus 1 is equal to n choose k plus 1, and so on. So this equation become, the left side become 1, the right side also is 1. So you have equality. So this means that if the conjecture is true, then this inequality is in a way tight. That is indeed the best result possible. And later in the talk, we actually see that this condition if is actually if and only if. That if this has equality, then every k plus 1 subset must be independent. And that is a very short overview on Mason's conjecture. Is everybody happy with the statement? Is everything clear? Good. Okay, then let me continue. And now let me start with, let me do a very short, very simplified history of Mason's conjecture. And a big breakthrough for this conjecture was made by Hu, and Katz in 2015. So 2018 here is the journal publication date. And they show that for every matroid, that this sequence ik is indeed log-concave. And this was done by using the combinatorial host theory for matroid. So they take ideas from algebraic geometry and convert it or maybe refine it so that it can work for matroid. This idea is pushed even further in a next paper by He, Schroeter, and Wang, where they show that, yes, the second Mason conjecture is true with this extra constant of 1 plus 1 over k. This constant comes from using combinatorial host theory, but they don't apply it to the independent sets directly. They applied it to this thing that we call the positive correlation bound. And when they apply it to this some more refined structure, it turns out that this number 1 plus 1 over k just pop out at the end. And they don't only stop there, so they took this even further. And in 2018, again, the 2020 is a journal publication date, Anari, Liu, Oves, Garan, Vinzan, independently with Brándën-Huh, so they are two independent groups, they managed to solve the Mason's conjecture, the strongest form of Mason's conjecture. And in fact, actually, their paper appeared in the archive at the exact same date. And I was told that by one of the authors here that that is not a coincidence, that they actually arranged for that to happen. Okay? And what they do here is a bit different already from what they do for the first and second Mason. That here, they instead develop a polynomial theory that's called the Anari, and Anari groups call it the strong log-concave polynomials. Brándën-Huh call it Lorentzian polynomials. And building on their work, in 2021, Murai, Nagaoka, and Yazawa managed to show the characterization of equality for the third Mason conjecture. They show that this thing has equality if and only if every k plus 1 subset is independent. So remember that Mason already know that this thing, the if part is already known by Mason, that you can get equality if every k plus 1 subset is independent. So the contribution of Murai, Nagaoka, and Yazawa is to show that no other cases are possible. This is a very short, very simplified version, very simplified history of Mason's conjecture. And of course, I do not mention many important works, many amazing works by many other authors because of time constraint, and for that, I apologize. But before I proceed further, are there any questions about this history? Yes, Bethel? I would say that it does not immediately follow from the proof of on the proof of either groups. So there is some things that need to be done. Whether or not it's hard is of course subjective question. Okay, any other question? Thanks for the good question, Pavel. Oh. Good. Okay, if everything is good, then let me just quickly go back a little bit. Let me go back to Mason 1 and Mason 2. And here we see there's an evolution of ideas between Mason 1, 2, and Mason 3. In Mason 1, things are done mainly by algebraic geometry, which is of course very nice. It has a lot of structure, but it also means that it is a bit rigid. So it kind of limits our application. And we see that in Mason 3, the algebraic part is reduced. That things get more flexible, and because of that, it's allowed to prove more. That's why we have polynomial theory here. And today, what I want to talk about is that we want to take this direction even further. We want to make the proof completely linear algebra, completely elementary. That this thing can become more flexible and it can prove more. That is what we want to do. And the result of doing that is what we call the Combinatorial Atlas. By doing this, by making the proof completely linear algebra, completely elementary, we managed to prove some known inequalities, some known inequalities, and refine them for matroid, for most matroids, and for Stanley's inequality. Furthermore, we also managed to prove new log-concave inequalities that is not known before, which is for discrete Fourier matroids, for poset antimatroids, and for branching greedoids. In fact, we actually prove it for a more general family of greedoids, which is you can think of as a non-commutative version of matroid. And not only that, as long as you can prove log-concave inequality, it turns out that this Combinatorial Atlas comes built in with a way to check exactly when equality occurs. So in all these 6 cases, we get the log-concave inequality. We know exactly when equality occurs. That is what we did. And of course, it's impossible for me to cover all 6 of them because we don't have 1/4 of classes today. So forgive me that I will only focus on 3 of them today. Any questions so far, or from the online audience? Good. So let me continue, and let me now do the refinement for matroid. And if you want to go directly to the full refinement for all matroid, things can be a bit tricky. That things can be very technical. So let us just do a quick warm up for a very special case of a graphical Metroid for when k is equal to the number of vertices minus 2. In this situation, we can improve the bound from before, which is 1 plus 1 over n minus k, all the way up to 3 over 2. And furthermore, we know that this has equality for graphical Metroid if and only if the graph G is a cycle graph. Okay, and let me our bound is of course numerically better, but I want to say that this is also asymptotically better, in the sense that if you look at this ratio, ik squared divided by ik plus 1 times ik minus 1, and suppose that your graph, you take it so that the number of vertices, number of edges minus number of vertices goes to infinity. So this means that the graph is in a way dense. In this situation, our bound, it gives us 3 over 2 as a lower bound in the asymptotic. While the Mason tree, if you only use the Mason tree, what you get is simply 1. So this shows that our bound is better numerically and asymptotically. Yeah, so Pavel's question is that whether this is what is the value of k here? Is it only for number of vertices minus 2, or for all k? And the answer for this one is only for k. Only for the number of vertices minus 2. There is a version actually for any other k, but the number is not as nice anymore. It's not 3 over 2. It's some function of k. It's still bigger than 1. Oh yeah, yeah. Remind me to repeat the question so that the people in the online can hear it. Okay, if everybody's happy with the warm up, let us go to the full refined version. And for that, I hope that all of you can stay with me because this can go a bit technical. Let me apologize here first. And a loop is an element of a matroid X, such that the singleton, so the set containing that single element, is not independent. In the case of graphical Metroid, that means that you have a loop X. That's why it's called a loop. And 2 norm loops, or 2 proper edges in the case of graphical Metroids, they are parallel if when you take the set containing the 2 elements, the resulting set is again not independent. For example, these 2 edges are parallel to each other. because the union form a circuit which is not independent. And it turns out that two non-loops we can define an equivalence relation. We can say that two non-loops are equivalent if they are parallel to each other, and turns out that there's a parallel turns out that is an equivalence relation, and a parallel class is simply an equivalence class, and is an equivalence class of that relation. For example, in this graph, there is 3 parallel classes. Because the loop is not counted, we have edges 1, edges 2. These 2 edges is counted as 1. That's why we have 3 in total. The next one is that I need to define what is the matroid contraction. And for this, we need to think about the contraction for a graph. Formally, suppose that you have an independent set, let's say S. The contraction of a matroid M with respect to S is where you restrict only to the independent set that contain S. And then you remove S from all of them. The resulting collection turns out to still satisfy the exchange property, turns out to still satisfy the hereditary property. So it defines another matroid. In the case of graph, this is the same as, suppose that you take these 3 red edges, let's say they're independent, you take their contraction. The resulting graph, if you look at the matroid, the graphical method of resulting graph, that is the same as this contraction MS. And parallel S, we define this to be the number of parallel classes of the matroid where you contract by S. So it is a function of S. For example, if S is these 3 red edges, then the contraction, then the parallel S is this graph with 7 edges. That's why the parallel S is equal to 7. And I promise this is the last slide, the last technical slide. The k parallel number, where k is an integer, this is the maximum over all, the maximum of parallel S over all independent set of the same size. For example, here is all the independent sets of size 1 for our graph. We compute the parallel S for each one of them by using the method from the previous slide, which is 2, 2, 2, and 3. The k parallel number for k equal to 1 is therefore equal to 3, because the maximum of 2, 2, 2, 3 is 3. That is all the technical details we need. And now, wait, before I proceed, are there any questions? Is everything clear? You can see that Jason is happy. I think everybody is also happy. Okay, let us continue. There's a question? Okay, so now we are finally, we can finally state the refinement. So for all matroid, for general matroids, the Mason tree, where the constant here is n minus k, can be improved, where the constant becomes the parallel number of k minus 1 plus 1. Sorry, this is supposed to be minus 1. There's a typo here. And this is a definite improvement. This is a strict improvement, because if you follow the previous 3 slides, you do the calculation carefully, then the parallel number of k minus 1 is always bounded from above by n minus k plus 1. That is why we say this is a refinement. Okay, at this point, we have a refinement for the inequality. So some of you might ask, okay, how about equality? We do know something about equality for the previous Mason tree. What about in this case? And unfortunately, or maybe fortunately, there is a much richer structure for equality when it comes to this refinement. The one that we already know, which is when the PRL k minus 1 is the largest possible of the n minus k plus 1. This is known by the Murai, Nagaoka, Yazawa. This is when every k plus 1 subset is independent. But there's only one extreme. We go to the other extreme when the parallel number is as small as possible. We also already know from the warm-up that this is when the graphical matroid, when graph G is a cycle. But these are not the only thing. There are still something in the middle, something intermediate. For example, if you look at the full realizable metroids over a finite field FQ, in this case, we again get equality, where the constant PRL k minus 1 that appears in the masonry, that appears in the refinement, is n over q to power of k minus 1 minus 1. And not only this, we also have another equality case, which is when your matroid is a Steiner matroid. And I won't have time to cover that, but let me just say that the number PRL k minus 1 is n minus k plus 1 divided by m minus k plus 1. The important point, the one point that I want to emphasize here is that there are many examples for equality. And that brings to a natural question. When we have so many examples, what is the unifying property? What is the reason, even though they all look so different, what is the reason why they can give us equality? Is there any unifying property? The answer is yes, we have. And in fact, it is an if and only if condition. That if you have this condition, like with all the previous matroids, then you get equality, and that is the only way where you can get equality. This condition is a bit, maybe at first looks a bit technical, but I like to think about this in terms of Iso-Parametric inequality. But remember that Iso-Parametric inequality says that if you have a geometric object, you want to minimize the surface area when the volume is fixed. Then your minimizer is a ball. But what is a ball in terms of geometry? A ball is a shape that is as symmetric as possible. That when you look at every angle, they all look the same. In the idea of matroid, this condition is the same as saying that your matroid is as symmetric as possible. In the sense that for every independent set of size k minus 1, this S has the number of parallel classes equal to parallel k minus 1, the largest number possible. Not only that, every parallel classes of this S has the same size. That is what we mean to be as symmetric as possible in terms of matroid, in terms of this Mason's in this log-concave inequality. Okay. Before I proceed further, are there any questions about matroid before we leave matroid? So Papa is asking what we do if we can we do something like co-parallel instead of parallel? And okay, so my answer for that is that we don't think there's a connection. This is something that we have never explored. So at least at first glance, I don't see why I don't see how to put a co-parallel into the picture. But thanks for the suggestion. We will try to think and see if we can do it. Yes. So this parallel S, this parallel k minus 1 is indeed what Tom is described, which is contraction by S. Any other question? Any other question? Okay, seems like everybody's happy. Okay, so if everybody's happy with matroid, now let us leave matroid and go to the world of poset. Okay, just as promised. And a poset is simply a set with a partial order on the elements. For example, here is a 4-element poset. Elements are A, B, C, D. And we draw an arrow from one to the other if the former element is smaller than the later element in the partial order. For example, this means that A is less than B, A is less than C, B is less than D, and C is less than D. B and C are incomparable because there are no arrow. But here, there's actually one more relation, which is that A is less than D. This is because, remember, by transitivity, A is less than B, B is less than D, and therefore A is less than D. I just don't draw the arrow here because this is already implied by this equation over here, by the other two arrows. This picture is what we call the Hesse diagram, which will also appear again later. And a linear extension of a partial order is simply a completion of the partial order. That means that we order everything from the smallest to the largest. We complete it. For example, for this particular partial order, there are two possible linear extensions, either A, B, C, D, where A is the smallest, D is the largest, or A, C, B, D. And we will write that the Lx, L is a linear extension, X is the element of poset, is equal to an integer k. This means that X is the k smallest element in your extension. Okay. And the log-concave inequality, it appears very naturally from the poset in the following way. First, we need to fix the element z in the poset. Now, nk here is a number of linear extensions such that z is the k smallest element in the extension. Then, turns out, by Stanley in 1981, he shows that this sequence n1, n2, n3 up to nn is log-concave. And how he proved it is actually very elegant. It is actually arguably a one-page proof, where Stanley used an idea from geometry, the Alexandrov-Fairchild inequality. It's an inequality that you apply to polytopes, and the polytope that Stanley used is what we call the order polytope, where every region, every chamber of this polytope corresponds to one linear extension of the poset. You apply that, and magically, this inequality just pop up right at the end. Very nice proof. And in the same paper, Stanley is asking what will be the condition for this inequality to be an equality. This question, which sounds very simple, turns out to actually be very hard. And it was only solved last year in May 2020 by Senfeld and Brándën-Huh, where they show that this inequality can be equality if and only if these three numbers are equal. That nk is equal to nk plus 1 is equal to nk minus 1. How they prove it is that they actually managed to classify, not only for Stanley inequality, they classify all the extremals of Alexandrov-Fairchild inequality for all convex polytopes. Then they specialize it to order polytope, and after some arguments, they managed to get this condition out at the end. That is what is known so far about Stanley's inequality. Any questions? Everybody's happy with Stanley's inequality? Okay. If everybody's happy, then let me just say something. Let me just say something that we are not exactly too happy about. Okay, so the question is, can this inequality be expressed in terms of the poset? The answer is yes. In fact, in the paper of Senfeld and Brándën-Huh, there's actually a three condition. That this is if and only if this condition, if and only if another poset, another combinatorial condition. The combinatorial condition, I want to apologize that I don't include it because it's a bit too long to be put in this slide. But yes, it can be done purely combinatorially. Oh. Okay. Okay, and then I would like to Yair, I would like to apologize. I hope you don't mind. I exclude the last combinatorial condition. Any other questions? Okay, and now let me just say that. Okay, I need to be careful now. If there's one thing that we are a bit disappointed with this Stanley inequality, is that it's done by geometric way. That the Alexandrov-Fairchild inequality is used as a black box. So this makes the proof at least somewhat mysterious from the combinatorial point of view. Okay? That's why, in order to fix this, in order to remedy this, what we do is that we give a new combinatorial proof for Stanley's formula, for Stanley's inequality. And furthermore, we extend this to a weighted version of it. Here is what I mean by that. So a weight here is simply a function, let's call it W. It sends the element poset to let's say that's a positive integer, just to be non-technical. We say it's order reversing. If the weight of x is greater than the weight of y, whenever x is less than y in the poset. If x and y incomparable, then there's no condition. This weight can be extended to linear extension by taking the product of all of the weight in the extension of elements that is less than z. For example, in this linear extension AZBC, the weight is equal to the weight of A, because A is the only element that is less than z. While for the second one, the weight is a product of A and B, because A and B are both smaller than z. Then my claim is that counting this thing by uniform is not the only way. We can count it by this weight W instead. And it turns out the resulting thing, if you fix the W, you fix the weight, and let K goes from 1 to n, again, you get a log-concave inequality. And just like with the case of standard inequality, we can also characterize the equality case. We can also characterize the equality case. But in this case, the only changes is that rather than having divided by 1, we need to rescale everything by s, where s is given to you by your weight function. In the case when the weight is uniform 1, which is the case for the original Stanley, this s becomes 1, and when we recover the result of Yair, the result of Senfeld and Van Hendel. And of course, just like with before, there's a question about whether this condition is a combinatorial condition. The answer is yes. There's also a combinatorial condition that I omit here to save space. Any questions so far with Stanley inequality?
Is there a geometric?
So yeah, so your question is there a geometric proof of this from the using maybe mixed volume inequality? And my answer is that we have tried the way that you suggested, and if you do the rescaling that you suggested, that everything is rescaled by the same constant. So you are just adding a constant for every linear extension. So that will give this number. There might be another smarter way, maybe some deformation of that can give this result. That is an interesting question that we have not done yet, but maybe somebody can do it. Any other question? Yes? Yes? Yes.
The inequality, log-concave inequality, is it term by term?
Is it term by term?
We have the order reversing condition, right?
Yeah.
Otherwise,
Yes.
Okay, so you need that these are real numbers.
Exactly, yes. So yeah, that's the order reversing condition.
They're not formal variables.
They are not formal variables. Yeah. Oof. Thanks, Pavel. Okay, so seems like everybody's happy with this thing. And before I continue, let me just maybe ask a question that some of you might have in mind, just that you are too polite to ask it, which is that, hey, Swee Hong, you just keep showing us, maybe it's a refined, but it's still a known inequality. Can you show us something new? Well, that is a very reasonable question. That's a very reasonable request. That's why here is something new for poset anti-matroids. And we actually have this for something more general, but today let me just focus on the case of poset to make things simple. Okay? Require less notation. So here, alpha is a word where the letters come from the elements of the poset. So for this poset, the elements are A, B, C, D. So this means that your word, the letters will be from A, B, C, and D. And we say that a word alpha is feasible if there are no repeating elements. For example, AA is not feasible because A repeats twice. And also such that whenever a letter Y occurs in your word, and you know that X is strictly less than Y, then you must have that X occur in alpha before Y. The way I think about it is like with my sister, that if I get a present, then my sister must get a present, and not only that, he must get a bigger present. For example, the word BC is not feasible. Because why? Because remember, A is less than B, A is very jealous. If you have a word with B and C, he must also appear in the word. So this is not feasible. BA is also not feasible, even though A already appeared in the word, because remember, A is a very jealous person. Not only he appears, he must appear before B. So that's why AB is feasible, but BA is not. This is actually a part of a general setup that's called greedoid, but today let me focus only on the case of poset. And I want to count the number of feasible words, but I don't want to do it using uniform weight. I want to do this by using this weight that I call the chain weight, because uniform weight is overrated. Okay, let's get it. So this weight is where you count the number of maximal chains that start with an element. For example, in this poset, there are two maximal chains that start with A, ABD or ACD. So this part and this part. That's why the weight of A is equal to 2. BCD, just by coincidence, that the maximum weight turns out all to be equal to 1. Okay. And now that we have a weight on letters, we can extend this to weight on words by simply taking the product of the weight of the letters given over here. That is how we define the weight of a feasible word. Okay. And now the question is like this. Suppose that now I count the number of feasible words of fixed length of k, but I count it by using by the chain weight, not by uniform weight. Then it turns out that this sequence f omega k, when omega is fixed, k goes from 1 up to n. This sequence is indeed log-concave, as you might have expected, because today's talk is all about log-concavity. And we also have a way to actually find the equality. And for this one, let me just say that suppose that you know equality occurs for k equal to not only one of them, but actually for 1, 2, 3, 4, up to the height of poset minus 1. Then this can happen, this can occur if and only if when you draw the Hasse diagram of the poset. This becomes a forest. So this is just a tree. In general, it can be a forest, like collection of disjoint trees, where every leaf of the forest is of the same level. And here, let me just mention that we actually have a condition for specific value of k. But here I take the k to be 1, 2, 3, 4, 5. That's because for this particular situation, the statement is prettier. The statement is more elegant. The statement for the specific k is slightly more complicated. That is the result we have for poset antimatroids. Any questions so far? Everybody is also still happy? Okay. Okay. If everybody is still happy, then let me stop with the result and let us talk about the more important thing, which is how we actually prove this. Remember that our proof, what I claim is that the proof is combinatorial. The proof uses only linear algebra. Here is how it works. Oh, but yeah. The strategy is that first we need to build an acyclic digraph. And every vertex of this graph, they are associated with a non-negative symmetric matrix M and a non-negative vector H. So here's an example. This is an acyclic digraph. That's an arbitrary one. I will call the vertices at the top one, the top vertices, or also the spots vertices. The vertices at the bottom is what I will call the bottom vertices, or the sink vertices. And remember that because this is a combinatorial atlas, that means that if I zoom into these 4 vertices, I will see the matrix and the vector that's associated to it. So here is a 3 times 3 vector and a 3 times 1 vector. A 3 times 3 matrix and a 3 times 1 vector. And at this point, the choice of this matrix is just arbitrary. But in general, if you want to prove log-concavity, if you want to have a nice result, then this matrix needs to be special. they need to come from specific combinatorial data of your matroid or your poset. How you get from the poset into the atlas can be a bit complicated. But here is an example. Okay? And let me just choose a very simple poset of 3 elements, x, y, z, for standing inequality. And z here is in red because remember, in standing inequality, 1 element is fixed. This z is that fixed element. The combinatorial atlas, I mean the matrix that's associated to this particular poset, no, z is incomparable. There's no arrow here. Yeah, and the matrix that's associated to this particular atlas is 4 times 4. This is because it's labeled by x and y. X and y are the elements that's not in z. There are 2 copies of them, minimum and maximum, both for the rows and columns. It's 4 times 4. The rule is that every number in this matrix, they count linear extension with some special properties. For example, this green number 1, it comes from counting linear extension such that the y element is the minimal element of the poset because it's at the row of y min. It's in the row of x max. It means that x must be the largest element in the poset. Out of all linear extension of this particular poset, there's only 1 of them that satisfies this property, which is this poset that I color by green. That's why we put a number 1 over here. I claim that all of these numbers can be defined in this way. The exact definition is quite complicated. That's why I don't put it here. But I hope that this is enough to convince you that there is a way to convert the poset into the combinatorial atlas. You mean this entry? So this entry, the row is x minimum, the column is y minimum. This means that x and y, so x will be the smallest element, y will be the second smallest element. That's why we have a distinction between min and max. So if x and y are min together, that means that they need to be both. No, this is symmetric, right? So both the label for the row and for the label of column is the same. Yeah, that's yeah. So okay, that's a good question. So that this question is not exactly symmetric, and the answer is because yes. Why is top left entry is equal to 0 instead of 2? Good question. So this is labeled by x minimum and x minimum. This means the definition would be that it counts the number of extensions such that the first smallest element is x, the second smallest element is also x. But that can never occur. So that's why it's 0 in this case. Yeah, I hope this answers your question as well, Greta. Okay, if this is good, let me continue. Okay, so now we already know how to build the combinatorial atlas. The vector h, oh, I forgot to include it here. So for this particular case, the vector h is 1/2 for every point. So it's just 1/2, 1/2, 1/2, 1/2. But that is because our poset is very simple. In general, this thing can be pretty complicated as well. In general, how we determine for poset is that there's actually will be an extra parameter t, where everything minimum will be t, everything that's maximum will be 1 minus t. That will be our vector, how we get h. Any other question? Okay, no. Okay. So suppose that now we already have our combinatorial atlas. We need to do something with it. And our goal is to show that every matrix M here has hyperbolic inequality property. What this means is that suppose that for every, let's just say that X is any vector, Y is any non-negative vector. Then the bilinear form of M applied to X and Y, you square it, this is greater than or equal to the inner product of M by X multiplied by the inner product of M by Y. This is in a way like the Cauchy-Schwarz inequality, except that the sign is reversed. Usually for Cauchy-Schwarz it's less than equal, here you have greater than equal. And here there's an important remark I need to make, which is that we are not the first people to actually realize that this is important for log concavity. It's already known since in the 30s. In particular, just very recently, this is used to get effect in the Lagrangian polynomials in the paper by Brándën-Huh. It's also used in the modern take of the proof of Alexander-Fencher inequality by Yair Seinfeld and Raman van Hendel, where again, this hyperbolic inequality property is a crucial component. Okay. And some of you might ask, okay, we have hyperbolic inequality property. How is that related to log concavity? The idea is that when we build our atlas, we need to do it in a very specific way. That's why the definition just now is a bit complicated. It's done in such a way so that ak minus 1, ak, and ak plus 1, the number in your sequence, can be written as an inner product of this matrix M with G and H, where M, G, H come in from your atlas. There are specific value that is specific input. And now that you have this information, it then follows that log concavity is just a special case of the hyperbolic inequality, okay? Where you plug in the specific value to get your log concave. That and okay, up till here, is everything still fine? Everybody stay happy? Okay, I saw nodding head, so I guess people are still happy. So let me continue. Okay, so now we know that our goal is to prove hyperbolic inequality rather than proving log concavity. And of course, this cannot be done for all atlas. You need some condition. Arbitrary atlas cannot get you cannot get this goal. And we show that you can prove hyperbolic inequality as long as you can verify these three conditions, ordered from the easiest one to the hardest one. The first one is called the irreducibility. It just means that when you restrict your matrix M to the support, that means that you exclude the 0 rows, exclude the 0 columns. The resulting matrix must be irreducible. This is usually easy to check. You also want H, at least some of them, maybe not all of them. You need them to be positive. Just some condition. The second condition is a bit more, is the following. I like to think about this as a statement that's saying that we can do induction on atlas. More precisely, suppose that you have a matrix M associated with a vertex B, and you don't know what is the matrix M. But suppose that you know the matrix for the children of M. Let's say it's M1, M2, and M3. Then you can recover M by using the following recursive definition. Okay? So in a way, it's saying that all of the information of this atlas is encoded by the children, by the bottom vertices. And the rest can be done by using induction, can be done recursively. Sorry. The third condition, which is usually actually the hardest condition to check, is saying that look at the inner product induced by M on every vector X. This thing is somehow bounded from above by the sum of the inner product created by the children of M. And you need to also scale this thing by H, where H is the given H vector. And this condition is usually the hardest one to check. In fact, so far, all of our application, we prove this combinatorially, in the sense that we look at this number on the left, on the right, we give a combinatorial interpretation. And we saw that there's an injection, more or less, from the right to the left. That is why this number is non-negative. And one more thing I want to add is that in the case of Metroid, we are a bit luckier that this is actually always an equality. The same appears for mixed volume. If we apply this to the external function inequality, this is also always an equality. It's only for something trickier, like with poset, that this becomes a sharp inequality. So those are the three conditions. Usually we spend some time to check it. But now, suppose that we're already done with checking all these conditions. Then here comes the fun part. Suppose that you know that all of the children, M1, M2 of the MR, has hyperbolic inequality property. We have this bottom to top principle, which says that the parent, the M, will also have hyperbolic inequality property. And this becomes very useful when we prove hyperbolic inequality, because remember, our goal is to show that every vertices has this property. But in practice, we don't need to do it for all vertices. So here is an illustration. Suppose that you already checked this for, suppose that you already checked this for all of the children. Then, rather, usually for checking for the children is easy, because the bottom vertices is designed in such a way that they are described with a very simple combinatorial structure. That checking hyperbolic inequality is usually either calculation or straightforward. But then, once you do that, then you are done. Because then this structure is spread out. So that's actually the color that that once you have it for the children, the parent also got infected, and everything got infected. In a way, it looks like how COVID spread. The children got the COVID, the parent also got the COVID. Yeah. That is how we prove inequality. But now remember, I promise you not only inequality, I also promise you equality. Right? And for equality, we do the same thing, which is that we got our, what do you call this again? The Combinatorial Atlas. And again, the goal is that we want to show that same property holds for every vertex. But rather than hyperbolic inequality, we want this to be hyperbolic equality. Okay, where this is an equal sign rather than less than equal. And for this, we again have this power of spreading. But instead of spreading from bottom to top, now we spread from top to bottom. That means that if the parent has this condition, then the children also has this condition. And in application, this means that suppose that you already know that this parent has a hyperbolic equality, then this thing will spread all the way up to every children, up to every grandchildren of this atlas. An important thing here is that it doesn't spread to all children, but only to the children of A. And in fact, actually, it will actually be false. If we actually allow it to spread to all children, then it's known that this is a condition, it's a too strong of a condition in the algebraic, in mixed volume. And so that, okay, let me just do the conclusion now. In conclusion, what we have now is a new method to prove log-concave inequalities and also prove equalities if we can do it. The cost we pay is that we need to do this combinatorial atlas. We need to build this combinatorial structure. We need to verify some conditions. But once you do that, the payoff is tremendous. That everything else, the log-concave inequality, log-concave equalities, then follow automatically. And I think that is all I want to say for today. Thank you very much for the attention. Very good. Maybe people already asked the question in the talk. So yes, question? Can we actually characterize the mixed volume for external function inequality? Can we steal Yair and Ramon's lunch? The answer is actually no, we cannot. In the sense, yes, and the question. Yeah. Okay. The reason is actually we cannot is because of the following. Let me go there. So there is actually this condition, this technical condition of reducibility. And this means that we cannot do it for all polytopes. We cannot do it for all convex polytopes, but only for special polytopes. And those special polytopes turns out to be condition that's already known, and which is actually for the simple and strongly isomorphic polytopes. So what they do in the Yair and Ramon paper is that they actually managed to do this even for some other degenerate cases that cannot be captured, at least for now, because of this condition here. That would be my answer.
Want to prove inequalities about.
So the question is how or what?
How do you build poset?
How do we? Yes. So for the poset, let me just go back to the picture. For matroid case, this poset is what we call the poset of independent sets. So it's the simplicial complex of the independence complex. That will be this atlas for the matroid. For poset, this will be for poset, this is just the poset itself. The Hasse diagram of the poset itself. Any other question? Yes, Greta? Can we prove the Alexander function inequality by using this framework? The answer is yes, we can, but only for special polytopes. However, those special polytopes, it can be shown that other general convex bodies can be written as can be derived as a limit. So yes, in the sense that we can get the inequality, but there is this one extra step, which is to take the limit.
There's one more. How different is the general Atlas proof in the third case compared to this ultra-log-concave polynomial Lorentzian approach?
So the comparison between this Combinatorial Atlas and the Lorentzian polynomial. So I would say that the Lorentzian polynomial is a special case. It's a special case. Because, for example, as I say from before, if you go to this condition, let me go back, that this is an equality for matroid. And also, for matroid and for mixed volume. But in general, if you want to do poset, if you want to do this anti-matroid, want to do greedoid, this must be a strict inequality. So yeah, that would be my answer.
About the stronger result by Brándën of the proof.
Let me say what Igor said. So what Igor said is that I am too humble, that the okay. Okay, Igor doesn't say that. So Igor said that our approach is more technical, but also more broad. It's also broader. So that's why it can prove more compared to the other method.
Thanks, Swee Hong. Thanks, online audience.
Thanks again, everybody.